Hello everyone, today we will study matrix transformation. First of all, let me show you some basic concept. The symbol R represents the set of all real numbers, and we know that the set of all real numbers together form a line called a real line. And for the real line, we can think of the x-axis. X-axis is a real line from negative infinity to infinity. That's R, the set of all real numbers. And for example, we know that number 1 is a real number, number 2 is a real number, negative 3 is a real number, a half is a real number, square root of 3 is a real number, pi is a real number, e is a real number. They're all real numbers. That's R. R2. R2 is a real plane. Or we can think of the SY plane. R2 is a real plane, or we can think of the SY plane. That's R2. In general, we use a pair of numbers to represent points in R2. In general, we use a pair of numbers to represent points in R2. It's called ordered pairs. For example, 1, 2, that's an element in R2. Negative 3, 4, that's an element in R2. Square root 2, 1/3. Those elements in R2. We use a pair of numbers to represent elements in R2. What about R3? We know that R is a real line. That's a one-dimensional space. R2 is a real plane, which is a two-dimensional space. R3 is a three-dimensional space. In general, we use a triple of numbers to represent. Points, elements in R3. We use a triple of numbers to represent elements in R3. -1, -2, square root of 5. Radical 2, 1/3, pi. We use triple of numbers to represent elements in R3. And similarly, R4 is a four-dimensional space. R4 is a four-dimensional space. In general, we use 4 numbers to represent an element in R4. For example, 1, 2, 3, 4. Radical 2, 1/3, pi, e. We use 4 real numbers to represent an element in R4. Then in general, for Rn is an n-dimensional space. Rn is an n-dimensional space. Rn is an n-dimensional space. In general, we use n elements. We use n real numbers to represent elements in Rn. For example, 1, 1, 1, 1, 1. We use n real number together to represent element in Rn. It could be any real numbers. Or it could be S1, S2, up to Sn. They're n real numbers. That's an element in Rn. We use n real number together to represent element in Rn. And this element here, they are called vectors. Next, let me introduce vectors. What is a vector? In general, we consider elements in R, R2, R3, and Rn to be vectors. In general, elements in R, R2, R3, and Rn are vectors. So, elements in R, R2, R3, R4, Rn are called vectors. They are all vectors here. And in general, we can represent vectors in two different ways. In general, a vector can be represented in comma delimited form. Comma delimited form. Or vector column form, or column vector form. In general, a vector can be represented in comma delimited form or column vector form. For example, a comma delimited form looks like this. For example, vector 1, 2, 3. That's a vector in comma delimited form. -1, radical 2, 1/3. That's a vector in comma delimited form. Or 2, 3. That's a vector in comma delimited form. Or it could be 1, -1, 0, 0. Those are vectors in comma delimited form. Another form is called column vector form. We write each vector as a column. Write each vector as a column vector. For example, the vector 1, 2, 3 can be written as a column vector 1, 2, 3. That's called column vector form. This vector -1, radical 2, 1/3 can be written as -1, radical 2, 1/3. That's called column vector form. And this vector 2, 3 can be written as 2, 3. And the vector 1, -1, 0, 0 can be written as 1, -1, 0, 0. So those are called column vector form. Those are called comma delimited form. Every vector can be represented in these two ways. Next, let me introduce standard basis vectors. In general, we use E1, E2, E3, and so on. We use this vector to represent standard basis vectors. E1 is the vector has 1 in the first entry, zeros on all other entries. E2 is a vector that has 1 in the second entry, zeros on all other entries. E3 is the vector has 1 on the third entry, zeros on all other entries. In general, En is a vector that has 1 in the n entry, zeros on all other entries. They are called standard basis vectors. For example, in R, the standard basis vectors is E1 equal to number 1. This is a 1 by 1 matrix. In R2, the standard basis vectors are E1. E1 has 1 in the first entry, 0 in the second entry. E2 has 1 in the second entry, 0 in the first entry. And in R3, the basis vectors the standard basis vectors are E1. E1 has 1 in the first place, 0 in other places. E2 has 1 in the second entry, 0 in all other entries. E3 has 1 on the third entry, 0 on all other entries. Because in R3 we only use 3 numbers to represent vectors, so we won't have E4, E5, E6. We only have E1, E2, E3. In R2, since we use a pair of numbers to represent each vector, we only have E1, E2. We don't have the third place, so we cannot put 1 in the third place. There's only 2 vectors. There's only 2 vectors, 2 standard basis vectors. In R1, we only use 1 vector. We use 1 number to represent elements in R1. So that's the only standard basis vector, which is number 1 itself. 1 in the first place. We can have 1 in the second place, third place. And in general, in Rn, the standard basis element in Rn, the standard basis elements are E1 has 1 in the first place, 0 in all other places. E2 has 1 in the second place, 0 in all other places. And in general, En has 1 in the n place, 0 in all other places. That's called the standard basis vectors in Rn. There are n vectors. So here you can see that there is 1 basis vector in R1. There are 2 basis vectors in R2. There are 3 basis vectors in R3. And in general, there are n basis vectors in Rn. But why is those standard basis vectors so special? Why they are so special? Let me show another example. You'll see why they are so special. The x equal to S1, S2, Sn be a vector in Rn. Then x can be represented as a column vector S1, S2, Sn. This column vector can be split into n vectors. First vector S1 in the first place, 0 in all other places. Second vector S2 in the second place, 0 in all other places. And the n vector is 0 in all other entries. Sn in the last entry. For this vector here, for this column vector here, in the first column, the only variable is S1. In the second column, the only variable is S2. In In the third column, only variable is Sn. So here I can factor. In the first column, if I pull out S1, what do I get? If I pull out S1, I get 1, 0, 0, 0, 0, 0, 0. In the second column vector here, if I pull out S2, what do we get? I get S2 times 0, 1, 0, 0, 0, 0, 0, 0, 0. In the last column here, if I pull out Sn, what do I get? I get 0, 0, 0, 0, 0, 0, until the last column, last place, last entry is 1. So x equal to S1 times this vector. What's this vector? This vector is E1. This is a standard basis vector. This is E1. And this is what? This is E2. Has 1 in the second place, 0 in all other places. And what's this? This is En. It has 1 in the n place, 0 in all other places. So here you can see that if we know the standard basis vectors, E1, E2, E3, and so on, then for any vector x, I can always write it as a linear combination of E1, E2, E3, and En, using its own components, S1, S2, Sn. So for any vectors x, I can always write it as S1 times E1, S2 times E2, plus Sn times En. That's why those standard basis vectors are so special. Next, let me introduce function. What is a function? Let A and B be sets. If f assign each element in A to exactly one element in B, then f is called a function from A to B, denoted by f from A to B. If f assign each element in A to exactly one element in B, then f is called a function. Next, let's look at an example here. Determine whether f and g are functions from A to B. Look at function f first. Function f assign A to B. F assign A to exactly one element, B. F assign B to D. Here f assign B to exactly one element, D. F assign C to E. F assign C to exactly one element, E. And f assign D to exactly one element, which is E. We may assign two elements to the same element, but we must assign each element exactly once. So here, yes, f is a function. F assign every element in A to exactly one element in B. Yes, f is a function. Here, f assign A to B. F assign B to D. F assign C to E. F assign D to E. We may assign different elements to the same element, but we can assign the same element twice. So yes, f is a function. How about g? Is g a function? Let's look at function g. Let's look at g here. G assign A to exactly one element here, A. Here, G assign A to A, which is exactly one element. G assign B to two elements, B and C. Here, G assign B instead A to two elements instead B. So G is not a function. Since G assign B to two elements instead B, so G is not a function. Since G assign B instead A, to two elements instead B, to B and C instead B. Since G assign element twice, G is not a function. If G is not a function, we don't write it like this. We don't write G of A is A. This is called function notation. Since G is not a function, we don't put it this way. We don't write G of A is A. Since G is not a function, we don't write it this way. This is called function notation. Only when f is a function, we put it this way. If G is not a function, don't write it this way. This is called function notation. Next, let me introduce domain and codomain. Let f be a function from A to B. Then set A is called the domain of function f. Set A is called the domain of function f. And set B is called the codomain of function f. In the previous example, f is a function from A to B, so A is called the domain of function f, and B is called the codomain of function f. That's the domain and codomain. Next, let me introduce image and inverse image. Let f be a function from A to B, with x belong to A and y belong to B. If f of x equal to y, then y is called the image of x. Then y is called image of x. Y is called image of x, and x is called an inverse image of y. Sometimes it's also called pre-image. Inverse image is the same as pre-image. X is called the inverse image of y. So y is called image of x. X is called the inverse image of y. In the previous example here, f from A to B. Here, B is image of A. Image of A is B. Image of B is D. Image of C is E. Image of D is also E. So here we can see that every element in the domain has exactly one image. Two different elements may have the same image, but every element in the domain has exactly one image. Note, every element in the domain always has exactly one image. Now let's codomain. Image of A. Inverse image of A is nothing. Inverse image of A is nothing. So inverse image of A, this A has no inverse image. Inverse image of B is A. There's only one inverse image. C has no inverse image. C has no inverse image. D has inverse image B. Inverse image of D is B. Inverse image of E is C and D. Inverse image of E is C and D. So for every element in the codomain, it may have no inverse image. It may have one image. It may have one inverse image, or it may have more than one inverse image. For example, here A has no inverse image. B has only one inverse image. B and D, both of them has exactly one image, one inverse image. E has two inverse image. E has two inverse image. Every element in the codomain may have 0, 1, or more than one inverse image. Every element in the codomain may have 0, 1, or more than one inverse image. For example, in the previous example, for A and C, in B, A and C both of them have no inverse image. In set B here, A and C, both of them have no inverse image. B and D have exactly one inverse image. B and D, both of them, each have one inverse image. Inverse image of B is A. Inverse image of D is B. And element E has two inverse image. E has two inverse image. C and D in set A, they are both inverse image of E. Next, let me introduce range. Let f be a function from A to B. The range of f is a subset of set B in which every element has at least one inverse image. The range of f is a subset of set B in which every element has at least one inverse image. For example, here in step B, B, D, and E have at least one inverse image. So B, D, E form a subset of B. That's called a range of F. In the previous example, domain of F is set A, which contains elements A, B, C, D. codomain of F is set B, which contains elements A, B, C, D, E. And the range of F is a subset of B. Which is a set of B, D, and E. These three elements has at least one inverse image. Here, the set B, D, E form a subset of B, which is the range of F. In the subset, in the codomain here, B, D, and E, they have inverse image. So these three elements form a subset of B. This is called range of F. So range of F is in the set with these three elements, B, D, and E. Next, let me introduce transformation. Let F be a function from Rn to Rm. Then F is also called a transformation from Rn to Rm. If F is a function from Rn to Rm, then F is also called a transformation from Rn to Rm. Or we can also say that F maps from Rn to Rm. Or we can also say that F maps from Rn to Rm. Next, let me introduce operator. In a special case, if F is a transformation from Rn to itself, then this function F is called the operator on Rn. If F is a transformation from Rn to itself, then F is called operator on Rn. Next, let me introduce matrix transformation. Let me first of all show you a matrix. Let A be an m by m matrix, shown below. A m by m matrix means matrix A has m rows and n columns. So first row will be A11, A12 until A1n because there are n columns. Second row will be A21, A22 until A2n. And since there are m rows, last row will be AM1, AM2, and AMN. That's an m by m matrix. Next, let's think of this. If I want to multiply a column vector to this matrix, what size the column vector should be? If I want to multiply a column vector to this matrix, what size the column vector should be? Since it's a column vector, it has only one column. How many rows does it have? In order to multiply two matrices, the number of columns in the first matrix must be the same as number of rows in the second matrix. So it must have n rows. So n rows, one column. This is n by 1 column vector. So let's call this x1, x2, xn. So this is an n by 1 column vector. Now, if I multiply these two matrices, what's the result? If I multiply these two matrices, what's the result? This is an m by m matrix. This is an m by 1 matrix. If I multiply, the result must be a matrix with m rows and 1 column. So the result is an m by 1 matrix, which is also a column vector. The result is an m by 1 matrix, which is also a column vector. Let me call this column vector W1, W2, Wm. Since it has m rows. Next, if we consider this matrix multiplication as a function, if we consider this matrix multiplication as a function, then what's the input, what's the output? If we consider this matrix multiplication as a function, then this will be the input, this column vector will be the input, and this column vector will be the output. This column vector has n components, so this column vector belongs to Rn. This column vector has m components, so this column vector belongs to Rm. So if we consider the above matrix multiplication as a function, f, then this function f map from Rn to Rm. Since f map from Rn to Rm, f is called a transformation. Since f map from Rn to Rm, f is a transformation. Then f is a transformation. From Rn to Rm. With f of x equal to the matrix A times the column vector x for all x in the domain. Then for function f, we take this matrix A times the column vector x for all x in the domain. A transformation defined by matrix multiplication is called a matrix transformation. A transformation defined by matrix multiplication is called a matrix transformation. And here we can see that this function f is defined by matrix multiplication. So this function f is a matrix transformation. This function f is a matrix transformation since it's defined by matrix multiplication. Next, let me give you the formal definition for matrix transformation. Let A be a m by n matrix. Let TA be a transformation from Rn to Rm, with TA of x equal to matrix A times the column vector x. Then TA is called a matrix transformation. If TA is a transformation from Rn to Rm, with TA of x equal to matrix A times the column vector x, then TA is called a matrix transformation. And in general, if A is a m by n matrix, that means matrix A has m rows and n columns. M represents the dimension of the codomain. M represents dimension of codomain. N represents the dimension of the domain. If A is an m by n matrix, means A has m rows and n columns. Number of rows represent the dimension of the codomain. Number of columns represent the dimension of the domain. Next, let's look at an example. Let A be a 4 by 2 matrix. Part A, find the domain and codomain of the matrix transformation TA. Part B, let U and V be two column vectors. Find TA of U and TA of V. Let's answer part A first. Find the domain and codomain of the matrix transformation TA. How do we find the domain and codomain here? We know that the dimension of the domain is always the same as number of columns. The dimension of domain is the same as number of columns. Since there are two columns, domain will be R2. And we know that the dimension of a codomain is the same as number of rows. The dimension of the codomain is the same as number of rows. Since there are 4 rows in matrix A, the codomain will be R4. That's how we find domain and codomain. Dimension of a domain is always the same as number of columns. Dimension of a codomain is always the number of rows. That's how we find domain and codomain. Now part B. Let U and V be 2 column vectors. Find TI of U and TI of V. Let's find TI of U first. TI of U, by its definition, we know that TI of X is matrix A times the column vector X. So TI of U do the same thing. Take matrix A times the column vector U. Matrix A here is this 4x2 matrix. 3, 4, 1, 6, 2, negative 3, negative 4, negative 1. Column vector U is 2, negative 1. If we multiply, what do we get? If we multiply, we know that the codomain is R4. The result must be a 4x1 column vector. It must have 4 components. The codomain is R4. The result must be a 4x1 column vector. It must have 4 components. Let's multiply. Take row times column. 2 times 3 is 6. Negative 1 times 4 is negative 4. 6 plus negative 4 is 2. Next, row times column. 2 times 1 is 2. Negative 1 times 6 is negative 6. 2 plus negative 6 is negative 4. Next, row times column. 2 times 2 is 4. Negative 1 times negative 3 is positive 3. 4 plus 3 is 7. Next, row times column. 2 times negative 4 is negative 8. Negative 1 times negative 1 is positive 1. Negative 8 plus positive 1 is negative 7. That's TI of U. This column vector represents TI of U. Next, compute TI of V. For TI of V, by definition, we know that TI of X is matrix A times the column vector X. So for TI of V, we take matrix A times the column vector V. Matrix A is 3, 4, 1, 6, 2, negative 3, negative 4, negative 1. V is a column vector negative 4 and 2. Let's multiply. Take row times column. Row times column. Negative 4 times 3 is negative 12. And 2 times 4 is 8. Negative 12 plus 8 is negative 4. Next, row times column. Negative 4 times 1 is negative 4. 2 times 6 is 12. Negative 4 plus 12 is positive 8. Next, row times column. Negative 4 times 2 is negative 8. 2 times negative 3 is negative 6. Negative 8 plus negative 6 is negative 14. Next, row times column. Negative 4 times negative 4 is 16. 2 times negative 1 is negative 2. 16 plus negative 2 is positive 14. That's TI of V. This is TI of V. Next, let me introduce zero transformation. Let 0 be a m by n zero matrix. Then the matrix transformation T0 from Rn to Rm is called a zero transformation. T0 is called zero transformation. Why is that? Why we call T0 a zero transformation? It's because what's T0 of X? What's T0 of X? For T0 of X, by its definition, we use zero matrix times the column vector X. Zero matrix times column vector X is a zero vector. Zero matrix times the column vector X is a zero vector. Since T0 of X is always a zero vector, it doesn't matter what we put here. The answer is always a zero vector. That's why T0 is called a zero transformation. It maps everything to 0. T0 map everything to 0. It map all x to 0. That's why T0 is called zero transformation. Next, let me introduce identity operator. Let I be a m by n identity matrix. Let I be a m by n identity matrix. Then the matrix transformation T sub I from Rn to Rn is called identity operator on n. It's on Rn. Ti from Rn to Rn is called identity operator on Rn. Why is that? It's because what's Ti of x? What's Ti of x? For Ti of x, by its definition, we use matrix I times the column vector x. For Ti of x, by its definition, we use matrix I times the column vector of x. Since I is the identity matrix, identity matrix times x is x. Since Ti of x always gives the same x here, that's why it's called identity operator. Since Ti of x always gives the same x from here, that's why Ti of x is called identity operator. Next, let me show you some properties of matrix transformation. Let A be a m by n matrix, and let Ta from Rn to Rm be the corresponding matrix transformation. Then, for all vectors u and v in Rn, and for all scalar k, we have the following properties. Part A, Ta of the zero vector is always the zero vector, always equal to the zero vector. Ta of ku is always the same as k times Ta of u. And Ta of u plus v is always the same as Ta of u plus Ta of v. Let's prove it. How do we prove for part A? Ta of 0. By its definition, we use matrix A equal to matrix A times the zero vector. A times zero vector is 0. It's zero vector. That's part A. Part B. Ta of ku. By its definition, we use this matrix A times ku. Then, since k is a scalar, I can put it in the front. Since k is a scalar, I can put it in the front. It's k times au. A matrix A times the column vector u can be written as Ta of u. A matrix A times the column vector u can be written as Ta of u. That's part B. Part C. Ta of u plus v. Ta of u plus v, by its definition, is matrix A times column vector u plus v. Then since they are vectors, since they are matrices, I can distribute A. I get matrix A times u plus matrix A times v. And we know that matrix A times the column vector u can be written as Ta of u. And matrix A times column vector v can be written as Ta of v. That's a proof for these properties. Next, let me introduce linear transformation. Let T from Rn to Rm be a transformation. If T of u plus v equal to T of u plus T of v, and T of ku equal to k times T of u, for all uv in the domain, which is Rn, and for all scalar k, then T is called linear transformation. If T of u plus v equal to T of u plus T of v, and T of ku equal to k times T of u, then T is called linear transformation. If you compare this definition with the property of this matrix transformation, we can see that matrix transformation satisfies both properties of linear transformation. So we can say that all matrix transformation are linear transformation. Every matrix transformation is a linear transformation. So note, according to the properties of matrix transformation, every matrix transformation is a linear transformation. Every matrix transformation is a linear transformation. Because matrix transformation, by its property, it satisfies both conditions of linear transformation. So every matrix transformation is a linear transformation. But how about the other way? Can we say every linear transformation is a matrix transformation? How about the other way? Can we say every linear transformation is a matrix transformation? The answer is yes. That's the next theorem. Yes, answer is yes. Every linear transformation is a matrix transformation. The answer is yes. Every linear transformation is a matrix transformation. Let's prove it. Let T from Rn to Rm be a linear transformation. Then by definition here, then for all u and v in the domain, and for all scalar k could be any real number. Scalar k could be any real number. We have t of u plus v equal to t of u plus t of v, and t of ku equal to k times t of u. That's what we have so far. We try to prove T is a matrix transformation. Our goal is to prove this T is a matrix transformation. How do we show T is a matrix transformation? We try to show that there is a matrix A. There exists a matrix A such that T of x equal to A times matrix A times the column vector x for all x in the domain. That's our goal. That's how we show T is a matrix transformation. We need to show that there exists a matrix A such that T of x equal to matrix A times the column vector x for all x in the domain. That's how we show T is a matrix transformation, and that's our goal here. Now, how can we find a matrix A here? Let E1, E2, En be basis vectors in Rn. Let E1, E2, En be the basis vectors in Rn. Then T of E1, T of E2, and T of En belongs to Rm because E1, E2, En, they are elements in the domain. When I'm plugging elements in the domain, I get some elements in the codomain. So T of E1, T of E2, T of En, they are elements in Rm. So since they are elements in Rm, T of E1, T of E2, and T of En, they are m by 1 column vectors. Since T of E1, T of E2, T of En belong to Rm, then they are m by 1 column vectors. They all have m components, so they are m by 1 column vectors. So every one here is an m by 1 column vector. Next, let A be a matrix formed by column vectors T of E1, T of E2, T of En. Let A be a matrix formed by column vectors T of E1, T of E2, T of En. Then A is a m by n matrix with A equal to T of E1 in the first column, T of E1 in the first column, T of E2 in the second column, and T of En in the last column. Then A is a m by n matrix with T of E1 in the first column, T of E2 in the second column, T of En in the last column. Here we can see that matrix A has n columns. How many rows do we have? Each column vector are m by 1, so each vector has m rows. Therefore, A has m rows and n columns. Since A formed by these column vectors, A has m rows and n columns. Next, let X be a column vector with components S1, S2, Sn. Since X has n components, X belongs to Rn. Then, since E1, E2, En, they are basis vectors in Rn, X belongs to Rn. That means S can be noted as a linear combination of E1, E2, En using its own components. So S can be noted as a linear combination of E1, E2, En using its own components. Then S can be noted as S1 times E1 plus S2 times E2 plus Sn times En. Next, if I plug in X into function T, what do we get? If we plug in S into function T, what do we get? Here, X is S1 E1 plus X2 E2 plus Sn En. By the first property here, I can separate terms. Write it as T of S1 E1 plus T of X2 E2 plus T of Sn, En. Since T is a linear transformation, it satisfies both properties. So I can separate each terms, write it as T of first term, second term, and the n term. Next, by the second property here, I can always pull out a scalar. So pull out S1, S2, Sn. By the second property, I can always pull out scalar. So I pull out S1, I get S1 times T of E1. Pull out S2, I get S2 times T of E2. If I pull out Sn, I get Sn times T of En. That's T of x. Next, if I take A times x, what do we get? If I take this matrix A times x, what do we get? Here we know that matrix A is a m by m matrix. It's an m by m matrix, means it has m rows, n columns. So matrix A is A11, A12, A1n, has n columns. Second row, A21, A22, A2n. Last row is AM1, AM2, AMN. Means A has m row, n columns, m rows, n columns. That's an m by m matrix. Now, if I take A times x, what do we get? X is this column vector, S1, S2, Sn. Since A is formed by these column vectors, so the first column here is T of E1. Second column is T of E2. Third column is, the n column is T of En. Since those are column vectors in matrix A. So this column is T of E1. This column is T of E2. And this column is T of En. Now let's multiply. If I multiply the matrices, I take row times column. Row times column. So first row times first column here, we get A11 S1 plus A12 S2. Let me write x in the front. I have S1 A11 plus x2 A12 and plus xn A1n. That's first row times first column. Next, take second row times second column. We get S1 times A21 plus S2 times A22 plus Sn times A2n. Continue in the last row. Take the last row times this column here. We have S1 AM1 plus S2 AM2 plus Sn AMN. Then this matrix can be rewritten as X1 A11, S1 A21, and S1 AM1 plus S2 A12, S2 A22, and the last row is X2 AM2 plus Sn times A1n, Sn times A2n. Last row is Xn times AMN. In the first column vector here, we can see that S1 is a common factor. S1 is a common factor, I can pull it out. If I pull S1, I get A11, A21, AM1. In the second column, we can see that S2 is a common factor, so I can pull S2. If I pull S2, I get A12, A22, and AM2. In the last column, you can see that Xn is a common factor. If I pull Sn, what's left is A1m, A2, A1n, A1n, 2n, A2n, and AMN. What's this column? What's this column vector here? The column vector A11, A21, AM1, it matches the first column here. And so that's T of E1. Plus X2 times this column. This column vector matches the second column here. So that's T of E2. And keep going. We have Xn times this column vector. This column vector matches the last column here. So we have Xn times T of En. So matrix A times X is S1 times T of E1 plus S2 times T of E2 plus Sn times T of En. So matrix A times X is S1 times T of E1 plus S2 times T of E2 plus Sn times T of En. And here we can see that T of X equal to this. Ax also equal to this. They're exactly the same. So T of X equal to A times X, matrix A times column vector X. Since T of X equal to matrix A times column vector X, that means T of X is a matrix transformation. Since there exists a matrix A, since there exists M by N matrix A, such that T of X equal to matrix A times the column vector X, then T is a matrix transformation. That complete the proof. Since there exists a M by N matrix A, such that T of X equal to the matrix A times the column vector X, then T is a matrix transformation. Therefore, T is a matrix transformation. That complete the proof. So, every linear transformation is a matrix transformation. And also, every matrix transformation is a linear transformation. Keep it in mind. Every linear transformation is a matrix transformation. And every matrix transformation is also a linear transformation. And this matrix A here, note, in the above proof, the matrix A formed by column vectors T of E1, T of E2, and T of En is called the standard matrix. It's called a standard matrix of the transformation T. Of the linear transformation T. This matrix A, formed by T of E1, T of E2, and T of En, this matrix A is called the standard matrix of the linear transformation T. Next, let's look at an example here. Let the linear transformation T be defined as this. Part A, find T of 3, negative 2, 1. Part B, find the standard matrix of T. Part C, use the standard matrix to compute T of 3, negative 2, and 1. Let's do part A first. Part A, find T of 3, negative 2, 1. For T of 3, negative 2, 1, we plug in 3 for x1, plug in negative 2 for x2, plug in 1 for x3. What do we get here? If I plug in 3 for x1, I get 2 times 3. If I plug in negative 2 for x2, I get minus negative 2. If I plug in 1 for x3, I get plus 4 times 1. Next, again plug in 3, negative 2, and 1 for x1, x2, x3 in the second row. I get 3 plus 3 times negative 2 minus 1. Then simplify. 2 times 3 is 6. Double negative is positive. 6 plus 2 is 8. 8 plus 4 is 12. Second row. 3 times negative 2 is negative 6. 3 plus negative 6 is negative 3. Negative 3 minus 1 is negative 4. So that's the answer. It's T of 3, negative 2, and 1, which is equal to 12 and 4. Part B. Find the standard matrix of T. The standard matrix of T is a matrix formed by T of E1, T of E2, and T of En, where E1, E2, En, they are basis vectors in the domain. E1, E2, En, they are basis vectors in the domain. What's the domain here? In function T, what we input is a 3×1 column vector. So a 3×1 column vector contains 3 components. So the domain is R3. Domain is R3. So in R3, the basis vectors is the basis vector in R3 is E1, E2, E3. The basis vector in R3 is E1, which is 1, 0, 0. E2, which is 1, 0, 1. E3, which is, E2 is 0, 1, 0. 1 in the second place. E3 is 0, 0, 1. Those are the basis vectors in R3. Next, we plug in the basis vectors into function T. Plugging each basis vector into function T. What's T of E1? E1 is 1, 0, 0. So I plug in 1 for x1, plug in 0 for x2, 0 for x3. What's left is 2 times 1 minus 0 plus 4 times 0. 1 minus 1 plus 3 times 0 minus 0. If we simplify, we get 2, 1. That's a column vector 2, 1. What's T of E2? E2 is a column vector 0, 1, 0. If I plug in 0 for x1, 1 for x2, 0 for x3. If we plug in, we have 2 times 0 minus 1 plus 4 times 0. 0 plus 3 times 1 minus 0. If we simplify, we get negative 1 in the first row and 3 in the second row. Next, compute T of E3. E3 is the column vector 0, 0, 1. We plug in 0 for S1, 0 for S2, and plug in 1 for X3. I get 2 times 0 minus 0 plus 4 times 1. 0 plus 3 times 0 minus 1. Simplify, we get 4 in the first row, negative 1 in the second row. So those are the answers for T of E1, T of E2, and T of E3. Next, the standard matrix A is a matrix formed by column vectors T of E1, T of E2, and T of E3. The standard matrix A is a matrix formed by these 3 column vectors T of E1, T of E2, and T of E3. So in the first column, we write T of E1, which is 2, 1. In the second column, we write T of E2, which is negative 1, 3. In the third column, we write T of E3, which is 4, negative 1. That's the standard matrix of T. That's the standard matrix of T. That's part B. Part C. Use the standard matrix to compute T of 3, negative 2, and 1. So T of negative 3, T of 3, negative 2, and 1. If I compute this using standard matrix, I take matrix A, 2, negative 1, 4, 1, 3, negative 1. Take matrix A times this column vector, 3, negative 2, and 1. Then multiply. Take row times column. So first row times first column. 3 times 2 is 6. Negative 1 times negative 2 is 2. 1 times 4 is 4. 6 plus 2 is 8. 8 plus 4 is 12. We get 12 in the first row. Next, row times column. 3 times 1 is 3. Negative 2 times 3 is negative 6. Negative 1 times 1 is negative 1. 3 plus negative 6 is negative 3. Negative 3 plus negative 1 is negative 4. So that's how we compute T of 3, negative 2, 1 using the standard matrix. We get exactly the same answer as we compute it directly. Next example, let the linear transformation T be defined as this. Part A, find T of 4, 6. Part B, find the standard matrix of T. Part C, use the standard matrix to compute T of 4, 6. Let's do part A first. How do we compute T of 4, 6? When we compute T of 4, 6, we plug in 4 for x1, plug in 6 for x2. So we have 2 times 4 plus 3 times 6. That's the first component. Second component, we have 3 times 4 minus 6. The third component is 5 times 4. And the fourth component is 4 times 6. Then simplify. The first component, 2 times 4 is 8. 3 times 6 is 18. 8 plus 18 is 26. That's the first component. In the second component here, 3 times 4 is 12. 12 take away 6 is 6. That's the second component. In the third component, 5 times 4 is 20. In the fourth component, 4 times 6 is 24. That's the answer. That's T of 4, 6. Part B. Find the standard matrix of T. In order to find the standard matrix of T, we need to find the basis vector in the domain first. What's the domain here? For domain, look at the input. In function T here, we input 2 numbers. We input a pair of numbers. So domain is R2. Once we know the domain, find a basis vector in the domain. Find a basis vector in the domain. In R2, there are two basis vectors. E1 is the column vector 1, 0. E2 is the column vector 0, 1. Next, compute T of E1 and T of E2. For T of E1, plug in E1 into function T. In order to plug in here, we must write this column vector in comma delimited form. So this column vector can be written as 1, 0. That's the comma delimited form of a vector. So we plug in 1 for S1, plug in 2, plug in 0 for x2. I get 2 times 1 plus 3 times 0, comma 3 times 1 minus 0, comma 5. Let me put it in the second row. Two times 1 plus 3 times 0, 3 times 1 minus 0, 5 times 1, comma 4 times 0. Simplify. 2 times 1 is 2, 3, 5, 0. And write this as a column vector. Write T of E1 on the final answer as a column vector. 2, 3, 5, 0. In order to find the matrix, to find the standard matrix, write T of E1 as a column vector. That's the first column of the standard matrix. Next, compute T of E2. T of E2. E2 is the column vector 0, 1. In order to plug in, write this column vector in comma delimited form. Like this, 0, 1. Then plug in 0 for x1, plug in 1 for x2. We have 2 times 0 plus 3 times 1, comma 3 times 0 minus 1, comma 5 times 0, comma 4 times 1. Simplify. We get 3, comma -1, comma 0, comma 4. Then write it as a column vector. Write T of E2 as a column vector. We have 3, -1, 0, 4. Next, the standard matrix A is T of E1 in the first column and T of E2 in the second column. T of E1 and T of E2, they are column vectors of matrix A. Then plug in. T of E1 is 2, 3, 5, 0. T of E2 is 3, -1, 0, 4. That's the standard matrix T. That's the standard matrix of T. That's part B. Part C. Using the standard matrix to compute T of 4, 6. Compute T of 4, 6. We first of all write 4, 6 as a column vector. Since A is the standard matrix of T, I take matrix A times this column vector. Take matrix A times this column vector. 2, 3, 3, -1, 5, 0, 0, 4. Times this column vector, 4, 6. If we multiply, take row times column. 2 times 4 is 8. 3 times 6 is 18. 8 plus 18 is 26. 3 times 4 is 12. 6 times -1 is -6. 12 plus -6 is 6. Next, row times column. 4 times 4 is 20. 6 times 0 is 0. 20 plus 0 is 20. Next, row times column. 4 times 0 is 0. 6 times 4 is 24. 0 plus 24 is 24. We get exactly the same answer as we have here. So if we compute directly, or we find the standard matrix first and then multiply the matrix, we get exactly the same answer. Next theorem, let TA and TB be matrix transformations from Rn to Rm. If TA of x equal to TB of x for all x in Rn, then matrix A equal to matrix B. Let's prove it. Here we try to prove matrix A equal to matrix B. Let's find their dimensions first. We know that TA and TB, they are both matrix transformations from Rn to Rm. The dimension of the codomain always represent number of rows, and dimension of the domain always represent number of columns. Since we have m rows and n columns, both A and B, they are m by m matrices. Since TA and TB, they are matrix transformations. From Rn to Rm. Then both A and B are m by m matrices. Dimension of the codomain represents number of rows. Dimension of the domain represents number of columns. So here we know that both A and B are m by m matrices. Let A be the matrix with m rows and n columns. So let A be A11, A12, A1n, A21, A22, A2n. Last row is AM1, AM2, and AMN. And let B be the matrix. B11, B11, B12, B1n. Second row, B21, B22, and B2n. Last row, BM1, BM2, BMN. Both A and B in the m by m matrix. We try to show that they are exactly the same. That means all entries are the same. That means every entry must be the same. How can we show that? Let's first of all find the basis vectors. Let's first of all find the basis vector in the domain first. Domain is Rn. So let E1, E2, En be basis vectors in the domain. Let E1, E2, En be the basis vectors in Rn. Then, since TA of x equal to TP of x for all x in the domain, then we have TA of E1 equal to TP of E1, TA of E2 equal to TP of E2, and TA of En equal to TP of En. What's TA of E1? Since TA is a matrix transformation, TA of E1 is the same as A times E1, matrix A times the column vector E1. And TP of E1, by its definition of matrix transformation, TP of E1 is matrix B times the column vector E1. And similarly, TA of E2 is matrix A times column vector E2. TP of E2 is a matrix B times the column vector E2. And TA of En is matrix A times the column vector En. TP of En is a matrix B times the column vector En. Here, what's A times E1? What's matrix A times E1? Matrix A is a matrix A11, A12, A1n, A21, A22 times A2n, AM1, AM2, AMN times E1. E1 is a column vector which has 1 in the first place and 0 elsewhere. If we multiply, take row times column. So if I take row times column, what I get is A11, the rest is 0. Next row, if I take row times column, what I get is A21, the rest are zeros. Continue in the last row. If I take the last row times this column, I get AM1, the rest are zeros. So we get the first column. If I take matrix A times E1, I get the first column. I get the first column from matrix A. So matrix A times E1, I get the first column, which is A11, A21, AM1. Similarly, if I take matrix B times E1, I also get the first column, which is B11, B21, BM1. So in matrix A and B, their first column are exactly the same. Next, what's A times E2? Matrix A is A11, A12, A1M, A21, A22, A2M. Last row is AM1, AM2, AMN. That's matrix A times E2. E2 has 1 in the second place, zeros elsewhere. So if I multiply the matrices, take row times column, I get A12 in the first row. Next, take row times column, we get A22, the rest are zeros. A22, the rest are zeros. Then continue in the last row, take the last row times this column, I get AM2. The other entry are zeros. 0, 0, 0, the rest are zeros. So that's exactly the same as the second column. What we get here is exactly the same as the second column. So when I take matrix A times E2, I get the second column. So matrix A times E2 is the second column in matrix A. I get A12, A22, and AM2. If I take matrix B times E2, similarly, I got the second column from matrix B, which is B12, B22, BM2. Continue. If I take A times En, If I take A times E1, I got the first column. I take A times E2, I got the second column. Similarly, if I take A times En, I've got an nth column from matrix A. The nth column from matrix A is A1n, A2n, AMN. For B times En, similarly, I got the nth column in matrix B. I get B1n, B2n, and BMN. So here we can see that every column in matrix A and matrix B, they are exactly the same. If every column are the same, if every column is the same, then matrix A and B must be the same. If every column is the same, then matrix A and B must be the same. Therefore, matrix A equal to matrix B. That completes the proof.